In this lecture, I'm going to cover some theory and some relationships in the field of exactly in the field of nucleation, not even like a crystallization. So I know we already talked a lot about how nucleation works, how supersaturated solution looks like, how the molecules in the supersaturated solution looks like, and how the solid molecules they like to come together. They try to form some intermediate solute clusters. From there, we might get some stable nuclei, which should normally evolve into a full-length crystal. So these things we already learned in the previous lectures. So we never covered any theory. We never talked about some relationships that connect your process parameters with something related to your crystal nuclei. Yeah? So because we we tried we tried to cover the whole nucleation process just using some diagrams and some imaginations. So that's how we learned about nucleation so far. In this lecture, I'm going to introduce you a bit of theory. Yeah, it might look a bit complex because it is really a complex process. It's not easy to understand by reading just like that. Yeah, like you have to pay a bit of attention and then try to try to listen what I'm going to say, and then try to make a sense out of that. So whatever we talked about nucleation, that rule stands. Like you have some molecules, they will come together and then they will evolve into some single crystals. So that rule applies. But if you think that way, like I have some diagram here. So so these are your solute molecules. Where is the highlighter? Yeah, so I showed some solute molecules. Yeah, so they and just assume this is your supersaturated solution, and they all like to come together. They randomly come together, something like here. Just follow the highlighter, and then eventually you will form some stable crystals out of there. So I already called these parts as solute clusters, and then from the solute clusters you might get some stable crystal nuclei. So that's the whole idea. But let me change it to pen. So draw a new figure that will make it simple. So if you have a lot of solute molecules, obviously you have a solvent. I'm not drawing them. So just assume your solute molecules, they are going to come together, and then why it has, just imagine, and then they evolve into single crystals. Yeah? So let we call this as a nuclei, or let's call it as a stable nuclei. So stable, it means it's not going to dissolve back into the solution. So this is the general theory or general idea we have about nucleation. But but we can ask some questions. So when these molecules come together, instead of developing into full crystals, it can dissolve back into the solution, and this can happen. So this can happen, and either it can develop into a stable nuclei. So both these things can happen. So so we need to develop a theory, or we are not going to develop a theory. It's already there in the literature. It was developed by a very big scientist, Gibbs. Probably you all heard his name, Gibbs free energy. He developed some expression to that can tell, or that can give some information. So when this step happens, process one, where your solute clusters they evolve into a stable nuclei, or the process two, where all the solute clusters they dissolve back into the solution. So what Gibbs thought was like, So imagine these pairs are Gibbs assumed the molecules are spherical particles or spherical shape, and then he assumed like they all come together, something like that, and he thinks once the radius of the they come together to make like a sphere, and then what he assumed like if the radius of the sphere is greater than some value, he call it as critical radius. Then these clusters grow and then develop into a stable nuclei. So that will be your step one, something like here. And then the second possibility, which it can dissolve back into the solution, that can happen when all these molecules, spherical molecules, and if their radius, if they combine together, and if the radius is less than critical radius, they will dissolve back into the solution. Dissolve back into the solution. So that's the general idea Gibbs have in his mind. And using this simple idea, he proposed some, or he developed some expressions, so that which we are going to derive in this lecture. Yeah? So try to keep these things in the mind. So to understand this tough concept, all you need to think like the way how Gibbs used to think about the process of nucleation. So there are two possibilities. Either your clusters can develop into a stable nuclei, or either it can dissolve back into the solution. So that's how Gibbs thought, and that's how we are going to deal with this theory in this lecture. So let's go back what I wrote here. This one I already talked few times. Crystal is like a macroscopic structure. Crystal is like a macroscopic structure composed by ordered arrangement of unit cells. And then whenever I say this unit cell, it can refer to the like one of the many nuclei formed via crystallization. Say like either this can be your first nuclei, or the first nuclei can be more than one unit cell. So nobody knows this one. Yeah. So nobody knows whether the first nuclei is a one unit cell or it's more than one unit cell. So this is something like a one of the least understood things in the field of nucleation. So and why is that? Because for that you need to have a very good microscope, and that microscope can see something in the liquid. Yeah. So and these type of technologies were developed only in the recent years. Only in the last 10 years we have access to such type of tools. So it's not easy to know your first stable nuclei, whether it contains one unit cell or whether it contains more than one unit cell. Probably it can contain more than one unit cell. So these are the some basic things. We already covered this in the previous lecture. I already showed through some diagrams. Then I just wrote to remind you. So crystal nuclei may contain more than one unit cell. Just to remember this thing. Yeah, I showed it in like a 2D diagram. This is one unit cell. This is second unit cell. Third, fourth, fifth, sixth, seventh, eighth, and nine. Yeah. So all these 9 unit cells can be called as a stable nuclei. The first one, or it can be one unit cell, or it can be two unit cell, or it can be three and four unit cells. Yeah. So no one knows this, but you should remember stable nuclei is a crystalline material, and it may contain one or more than one unit cell. So try to keep this in your mind. And then few things that you should know when through this module is nucleation is amazing sometimes because you start from a solution and then you make a beautiful crystals out of the solution. All you do is like you create supersaturation and then wait, and then the system will take care of itself. The molecules will recognize themselves, and then at one some particular time or some particular point they will arrange themselves to make a perfect beautiful crystal. So in that way nucleation is amazing, but nucleation is also mysterious. So no matter if you do this nucleation experiment in a lab or in maybe in like a 100 ml reactor, or you do the nucleation in a big industrial scale reactor, say like 1,000 liter reactor, the behavior will be still mysterious. So why we call them as mysterious is like I showed some figure here. So just assume this is your crystallizer. Just follow the blue lines. So you created a supersaturated solution, and if your supersaturated solution is contains some impurities, it may take more than 24 hours to nucleate. So what happens in these 24 hours? The molecules, they try to look each other, they try to recognize each other, they try to find some comfort zone, they try to talk to each other. That's how declaration really works. It's not like a, if I'm saying like the molecules like to talk with each other, recognize each other, it's not a like a colloquial term. That's what really happened when it comes to nucleation. So and then after these 24 hours, out of nowhere, okay, 24 hours, sometimes it can happen in 1 minute, sometimes it can happen in 48 hours. So this is like a completely stochastic process. Nobody knows what can happen and when it can happen. But one thing for sure, molecules can recognize eventually at some point, and they will come together and they will make the crystal. So just assume that. So why we call it as mysterious process is like it takes after 24 hours. Just imagine, say like some 10 molecules, they come together and then they make the first stable nuclei. So if it takes 24 hours to make the first stable nuclei, and then it takes only less than the fraction of a second to make the remaining billions and billions of nuclei in the crystallizer. So that's how nucleation works. So you wait for some time, and once the system recognizes something, and then once it makes the first nuclei, out of nowhere the solution will turn cloudy. It turns cloudy because you manage to form billions and billions of crystal in the solution. So this is the mysterious part of nucleation. So you must know these things. You won't find this in the textbook. They won't say it in the textbook. You will realize only if you do the experiment by yourself. So this is the mysterious part of nucleation, and that's why it's so difficult to model. Because it's so unpredictable. Even if you have a good microscope, still it's unpredictable. First, you will never know when it's going to nucleate, and you will never know what's the number of particles inside the crystallizer, and you will never know how fast the first nuclei is going to trigger the entire event. So one nuclei, that's all you need to make billions and billions, or to give birth to billions and billions of nuclei inside the crystallizer. in this lecture, I'm going to show you a very important theory in the field of crystallization. It's called the classical nucleation theory. And then we will also see some relationships. In fact, we're going to see only one relationship that connects something that you can measure in the lab, like for example supersaturation. That one you can measure in the lab with some parameter which we cannot see with our naked eye. We call it as the critical radius of a stable nuclei. So we are going to find some relationship that connects some parameter which you can really actually measure in the lab, and with the some quantity which we can only imagine in our mind. So we will see one relationship, and then we will see one very important theory in crystallization. So I put it like a separate video because this is going to be slightly tricky, and you must have some extra bit of imagination, and you have to believe the theory because it's developed by Gibbs, and it was developed in the year 1940, and it works so far so good for almost every system that we study in the lab. So there will be some imagination, you have to imagine, and there will be some assumption, and they are just think they are valid, and that will help you to understand the whole nucleation process in a mathematical way. So that's what we are going to do in this lecture. I will try to explain how Gibbs really thought when he proposed this equation, and then we will go on to the classical nucleation theory, and then we will finish this lecture. Yeah, so I wrote something here. So what really happens in nucleation? If you listen to my previous lectures, you could get some idea. Yeah, so it's not obviously nucleation, the whole purpose is to purification, and obviously we purify by producing some new pure crystals. So but it's not just like that. So it's even bit more than that. We are not just creating new crystals. So that's something like a macroscopic observation, because you can see some crystals in the reactor, and you can say that nucleation is something that can produce new crystals. But if you want to give some scientific explanation, or if you need to imagine what's exactly happening in the solution, this is what actually this is what happens. So during nucleations, what we are doing is something like we are creating a new surface, because your crystals have some definite boundary. So we have new surface and some volume. And what is this, what do I mean by new surface? So that this new surface is something that bounds the volume of your crystal. Yeah, if you have a crystal, whatever the surface that bounds, if this is your stable volume and this is your surface, the surface that bounds that volume. So keep that in the mind. And then in fact the precise treatment should be like we are creating a stable volume because it's not dissolving back in the solution. That's why you can see the crystals. And the stable volume is bounded by a surface. Obviously it should be a stable surface, and then there must be some interface that separates the stable liquid, in this case we are dealing with crystals, from the bulk solution. So if you have solution outside these crystals, obviously you are going to have some interface that separates your bulk crystals from the solution. So I hope you all understand up to this point. And then something like a quick revision what these crystals are about. So crystals are something like a macroscopic structure. We call it as a macroscopic structure because they are sometimes they are like few microns, maybe say like 100 microns. These things you can see with your naked eyes. You know, we cannot see the details of the crystal, or the crystal faces, or the shape of the crystals, but you can see that with your naked eye the solution will look like something more turbid. So these are macroscopic structures composed by ordered arrangement of unit cells. And the first unit cell, if you want, we can define something like this. So it can refer to one of the many stable nuclei formed via nucleation directly from the solution. I hope you all remember how the nucleation works. So you have, if these are your solute molecules, and if this is your blue is your solvent. So during nucleation, what happens is like where solid molecules eventually come together and then they settle into stable nuclei. And this nuclei won't stop there, it will eventually grow. If you take one this, after some time this will grow into a big crystal which you can observe under microscope. So that's what it happens. This is the whole process, or what happens during the crystallization. And in fact there should be some intermediate step. So the molecules come, they arrange in a random way, and then they eventually settle into stable nuclei. So try to check my previous lectures in this topic, so you'll get some idea. So typically the nuclei refers to the first stable structure formed in solution, and this can be a single unit cell or maybe so this can be a single unit cell or maybe few unit cells. Yeah, so try to try to imagine this type of cases. So prefer to draw this way. So just assume these are your solute particles. So just assume they are dissolved in your solution. The initial step will be, they will be randomly arranged. They will come together, and then after some time they will recognize each other, and then they will settle into ordered structures. If it's a cubic crystal, it will settle something like this. So that will be your first it will be your unit cell. And what do I mean by this statement is the first stable nuclei. Nuclei is something, a stable compound. It won't dissolve back. It will exist in solution like in a crystalline form, or if you want you can call generally like a solid. And then this will, and what I state is like either the first stable material that we observe in the solution, it can be just this one unit cell, or it can be more than one unit cell. So this is something very least understood, how the first stable nuclei looks like. Is it composed by one unit cell, or is it composed by many unit cell? So this remained a mystery until now. I mean now it means like almost 2020. Yeah? And very recently a group from Japan, I think this was, I saw this paper only 2 months ago. They published this paper in the year 2021, almost at the end of the year 2020. I'm going to upload this article in Sulis, and then I'm going to upload the few videos which they captured. They use transmission electron microscope, very, very sophisticated technique, and then they monitor directly what happens if you, here we are drawing some pictures. So they, instead of imagining like you and me, they decided to make some effort to see what really happens under microscope, and somehow they managed. And these are the very first images ever recorded in this world that can show directly how the crystals or molecules assembles to stable crystals during the nucleation process. So I'm going to upload those video, so you try to watch it. So that should give you some idea. And then you will also, and we are in year 2021. Yeah, so far we generated so many Nobel laureates in chemistry, in physics, and only now we managed to crack this code. Yeah, so this is really, that's why when I started the lecture I said crystallization is a very tough topic. The books will give you loads and loads of statements, but they always fail to say that they are very difficult to observe, because we don't have that level of facilities to probe everything at atomic scale. So try to see that video. It will give you some idea how you start from something like here, and then you end up with some stable crystals. So you should watch that video. Then coming back to the topic of nucleation again, I already showed some figures. So just assume the red color ones are your solute and the blue ones are your solvent in this image. So during nucleation, this is what happens. You get a stable nuclei. So what really happens in a supersaturated solution? I already talked a lot of time using this type of 2D images. Like they like to come together, they make a nice stable, they form its first stable nuclei, which obviously it should grow with respect to time. So what really happens in a supersaturated solution? Like the solute molecules comes together, that's obvious, and then it will take some time to recognize each other. Then they will assemble themselves in a perfect, if you want we can call it as ordered arrangement. It depends on the people. Some book they call it as a perfect arrangement, few people they call it as ordered arrangement, to create the crystal lattice of the very first unit cell. So you can ask a few questions like why the molecules comes together. The answer is obvious. We have a supersaturated solution, so naturally the molecules are going to come together in order to to minimize the energy in the system, because we already loaded too much molecules, which is above the solubility limit. And then why the molecules eventually evolves into a stable nuclei or even a bigger crystal. So why I put this second question, if you go back to this diagram, so why they have to come together and why they have to grow? There is a, so imagine if you have some molecules, just assume these are your solid molecule, they can come together and then they can separate again. They can separate again, and then again they can come together. They can separate, they can disintegrate again. So what's the reason behind something which allows you to grow this stable structure or to develop this stable structure inside that solution? And that's a very difficult thing to answer, but someone already did that job. So the answer comes from the Gibbs free energy, or to be precise we call it as a net free energy required to create a stable nuclei. So this is, we are going to derive a derivation proposed by Gibbs in the year 1940. So this will give you some theoretical idea on why molecules come together. Obviously we know the reason because we are working with supersaturated solution, but why they evolve into stable nuclei and when they will dissolve back into the crystals instead of developing into stable nuclei. So this, if you go back here, molecules they like to move randomly here and there. So this is a random process. So sometimes the molecule they like to come together, sometimes the molecule they like to stay alone, sometimes the molecule likes to disintegrate back from this type of intermediate structure. So I said to you, so something comes together, something disintegrates, something comes together again, something disintegrates. All this process in fact actually happens in the supersaturated solution. So both of these events can happen. So you have possibility of molecules coming together, assembling together, which might evolve into stable nuclei. You have the possibilities of molecules coming together, instead of evolving into stable nuclei they can disintegrate back and then they get eventually dissolved in the solution. So keep these things in the mind, because we are going to derive some expression. It's a very tricky one. So if you understand this random process, the whole scenario here, then it will be easy to understand the Gibbs expression. So let's go to the derivation part. So let's derive this net free energy required to create a stable nuclei. So you have to have a lot of imagination. So only then you can understand this topic. If not, it's going to be very tricky. So I will go a bit slow. This one. So typically if you have a supersaturated solution, the solution will be in some energetic state or some state that keeps the bulk solution to remain in its liquid phase. So what do I mean by that? This is something like a theoretical statement, but you need to imagine some number. If you have some solution that solution remains in its own phase, like they remain in solution forever and forever, and it's going to be comfortable to be in that liquid phase. And that's because it is associated with some energy. If you want, you can give some number, some quantity. So if you want to be precise, you can say that that system have its some energetic state that allows the system to remain in its own state. Yeah. So if you have some solution, if you want, you can give some number, say 10 kilojoules per mole. So this is some energy. We call this as a free energy that allows you to that allows your system that allows the system to remain in its own state. So now here comes the tricky part, which is related to nucleation. So if you want to create a new surface or a new volume, to be precise, stable volume that have a boundary, then we need some energy in excess to that of the energy of the bulk solution. So we need some energy in excess to this number. So say like 10 kilojoules, we need some energy in excess to this number. So that's why we put it in theoretically, like we need some energy in excess to that of the energy of the bulk solution. So we need to create, obviously in nucleation, we need to create a new surface, which means we need to spend some energy and we have to do some work. So some work should be done to create that new surface out of nowhere in that bulk solution. So keep these things in mind. So why is that and what it means? So these are very difficult questions to answer. So what it means, whenever I say like we need to create a new surface, it means the system needs to create a new surface that bounds the stable nuclei. So it's not an easy job, yeah. So what it mean? It means like this is not how do you call, like this is not a spontaneous process. So when I say like the system needs to do some work in order to create that surface, which means it's not a spontaneous process, like it won't happen naturally. The molecules needs to come together and it has to do some work to create that surface, you know. So which means in the process of nucleation we are creating a new surface, and that's not a spontaneous process. That's what I mean. So keep that in the mind. It's not. And then let's go to the next one. We have to look at the other side. So if you want, on the other hand, the building up of volume, maybe let's go back to this diagram here. So if you see here, the solute molecules, they come together something like here, and then they try to build up. So that process, so the building up of volume, that is going to be a spontaneous process. Naturally, molecules likes to move randomly here and there, unless if it is a solid. So in solid, they remain intact, and that's why we call it as a solid. In gas, they repel each other, they fly away, they don't even like to come together or stay closer. That's why we call it as a gas. In liquid, it will have it has some restricted movement. They move together, they won't leave each other, but they can move together within its own space. So that's why we call it as a liquid state. So try to, these are very, this needs extra bit of mind to imagine, and that's how this world works. Yeah, you have to, if you want to understand anything in chemistry that involves solid, liquid, and gas, if you have that extra bit of imagine how they look like at atomic scale or molecular scale, then you will understand the whole physics of the process. Obviously, you will not understand the chemistry part, but you will understand the whole physics of the process. So try to keep these things in the mind. So this is the take-home message, or this is something that you should understand when it comes to nucleation. We know that to create a surface, we need to spend some work, or the system needs to do some work. But on the other side, the building up of volume, this is going to be a spontaneous process. So the moment you created the supersaturated solution, even if you don't touch the system, even if you don't agitate the system, or even if you don't do anything, if you leave the system to stay alone in a corner of the room, the molecules are going to do its own job, which is they are going to come together. They will try to feel each other eventually. So and then that's why this type of process we call it as a spontaneous process. And normally, which means we don't have to do any extra bit of work. So which means it will happen naturally, and even if you don't spend some energy, or even if the system doesn't perform any work. So keep these things in the mind. So now we have to think two things. So to create a stable nuclei, the molecules will assemble to form a volume. So this is the one process which is going to occur naturally, and then the system needs to spend some work to create a new surface from that volume. This part is not spontaneous one, but this is a spontaneous process. Yeah? If you understand these two, then you will understand the nucleation theory as a whole. It's not spontaneous. So typically, the net free energy required to form a stable nuclei. So if you want to create a stable nuclei in the solution, you have to build up the volume followed by the surface. Not followed, they occur in parallel. So some volume they will try to build up by assembling of all those molecules. Out of that, we are going to create some stable surface. So which means we need to do some work. The system needs to do some work, this part, to create a stable surface, and there will be some spontaneous process, which is the building up of the volume. And if you sum that one, delta G, that will gives the value that you need. So that will give the net free energy that we need in excess to that of the bulk solution to create your stable nuclei in that solution. So that's the whole idea. So this is not our imagination, that's how Gibbs thought. So this is in 1940. For many reasons, this works for most of the systems. If you nucleate any of the APA molecules, say paracetamol or ibuprofen or curcumin or any other compound that you could imagine of, at the end of the day, this rule applies for almost every system. So now we are going to draw some diagram. So this is the diagram by Gibbs himself. So this is delta G in the x-axis, and in the y-axis, and the x-axis we have the radius of the nuclei. So what do I mean by radius? I said you have some solute molecules in the system. Just assume this is your supersaturated solution, the solvent molecules. So they will come together. Just assume these are sphere. So Gibbs thought everything is spherical. Yeah. So he also assumed the molecules are spherical. Obviously, it's not real, but his assumptions are okay. This is not a circle. This is a spherical particle, yeah? Or spherical face, if you want. You can call it that way. And this is the radius. So R is the radius of the nuclei. Which is trying to get fully developed in the solution. So this R is related to some process which is happening at the molecular scale inside the solution. So this is R is nothing but the radius of the critical nuclei. So this is what Gibbs thought. So everybody knows this thing. Yeah? So negative delta G, that means your process is going to be spontaneous. positive delta G, it means they are not spontaneous. Sometimes you need to spend some work. I'm sure you might have learned this before. If not, just keep these things in mind. Negative delta G, that measures something which is happening spontaneous in the system. If it's positive delta G, obviously we should spend some work in order to create something inside that system. So keep these things in the mind. And then this is what Gibbs says. So to build up the volume, your delta G is going to decrease with respect to R. In fact, with respect, delta G should be proportional to R cube. So it's going to decrease. So what does that mean? What does that mean? If the volume becomes bigger and bigger and bigger and bigger, which are in other words the radius increases, the net free energy that you need to create a stable volume in that solution, or to create some volume in that solution, decreases rapidly. Decreases rapidly. So it decreases with respect to R cube, which means the curve will go more steeper and steeper and steeper and steeper, something like that. Yeah. So I hope I explained this correctly, because it's very tricky, very tricky, believe me. And then this is what Gibbs thought. This is for the volume part. This is going to happen naturally. All the molecules, they love to come together. Yeah? It's a spontaneous process. They love to come together in a supersaturated solution. Always remember this word supersaturated. So whenever we are talking about nucleation or crystallization, just to remember supersaturation. So that's the driving force. So this is what Gibbs, and now we can go to the surface part. So this is what Gibbs thought. Your delta G is going to increase with R. In fact, delta G will be approximately proportional to R square. So this curve will go something like this. Yeah? So what Gibbs really says by this way? So imagine you have once the volume becomes bigger and bigger, which means the radius is going to become more and more big. So this is V2. Say this is V1. This is some small volume. To build a stable surface around this, we need less amount of work to be done. This is going to be very tricky. Just you have to imagine. Yeah, I can't just teach you this is the Gibbs expression. This is blah 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 is equal to something plus something, and then I can finish this topic. But I just want to explain it because it's going to be very tough. And I know if you are pharmaceutical chemistry students, you are going to use crystallization at some stage in your life, and that time you might have this. Sometime you might remember what I said during this lecture time. That time it's going to be helpful. One is I know you are going to get good marks in the exam if you follow all these things. Apart from that, once you go to some job, if you are working in the field of API purification or something, crystallization and chromatography are going to be like your everyday job. So I will try to explain crystallization and chromatography, and now adsorption is also becoming very trendy in many pharmaceutical industries. So I will try to explain these topics more from practical point of view, so you will know what to do if somebody give you the job. And apart from that, you should also know this theory. So this is like a heart of the nucleation. So if you know this theory, if you know how this part works, the rest of the crystallization process, even if you decide to do a PhD, that time everything is going to be easy. So try to keep these things in mind. These are very tricky, but that's the only way to understand this process and that's how people really assumed while they were deriving this type of hardcore theoretical expressions. Yeah, so all they did is beautiful assumptions, and then they made a very elegant theory out of those assumptions. So coming back to this topic, so you have some free energy, and so what I mean, so come back to this diagram, sorry. So you have a small volume, so just assume everything is spherical, nothing is circle. Yeah? I don't know how to draw 3D image on a 2D plain paper. So to build a surface around this small volume, just say you need, say V1, somewhere V2 here. So to build a surface on a small volume, then we need to spend a less amount of work. But if we need to build a surface on a bigger volume of some molecules that already assembled in the solution, we have to create even a extra amount of work. Yeah? So that's the meaning of this curve. And normally, if the volume goes 1 times bigger, so that, imagine if the radius is 1, your delta G record will be something like 1 raised to the power of 2. Approximate number, this is not accurate. If your radius is 2 centimeter, then the amount of delta G that you need will be approximately equal to 2 square. That's the meaning. And if you come back down here in this line, just put some, let's change some color, somewhere here and here. So if the volume is small, that minus delta G, that will be somewhere around r cube, and that's how it works. Yeah? So if r is equal to 1, so minus delta G will be approximately equal to r cube multiplied by some number. We will see that what those numbers are. We are going to derive that one. Yeah? So just remember this number r cube, r raised to the power of 3, r raised to the power of 2. So these are not my theory. This is not my theories. These are the assumptions of Gibbs, and this is proposed by Gibbs, and that's what you are studying in this module. So I hope you all understand. So the key thing that you should remember is to create a stable, not stable volume. To create a volume, it's a spontaneous process. The system is going to do the job automatically. But to create a surface, then the system needs to definitely to do some work. It's not a spontaneous one, and that's why the delta G is something positive. So what does that mean? Delta G is something like the net free energy to create some surface in the solution, and delta G is something like the net free energy that you need to create some volume in that supersaturated solution. So this is as a function of R. So if we go back to this equation here, I said to you, to create a stable nuclei in the solution, the net free energy that we need in excess to that of the bulk solution is nothing but this quantity, which is not a spontaneous one, and the another one which is a spontaneous process. So it's sum of these two quantities. So if we want to calculate delta G, which is nothing but the net free energy that we need in excess to that of bulk solution to create a stable nuclei, all we need to do is we have to sum these values. This one, this, let's put some highlighter. You have to sum this line, your area line, or sorry, your surface line, surface area, or maybe, how do you call it? Not surface area, surface, and then your volume line. Let me change the color. So these two, if you sum both of these, you will get something like, let me draw it here. You will get something like this one. Just follow the pink line. So you will have a peak maximum. Keep the look at the dot. Just follow the pen. And if you come down, this R value, we call it as critical radius. It's called RC, R suffix C, critical radius. So before I ask it some question, what is that? I said like what it means or why is that. No, not this one. Somewhere I mentioned. Okay, I can tell it again. Before somewhere I mentioned like if you have some molecules in the supersaturated solution, why they can grow, they can come together, and then they eventually grow and grow and grow and grow and grow and grow forever, and then it can grow and then they can disintegrate back. So both of these events can happen. Yeah? In fact, we don't need both to create a stable nuclei, but we need something that in between. So the Gibbs free energy, what it states is like if you have supersaturated solutions with molecules like this, they will come together, and if the radius, if it's greater than RC, they will grow. It won't disintegrate back, and then eventually you will get a stable nuclei out of that. In fact, this RC is nothing but the radius of your stable nuclei. This is approximate number, yeah? Because all the theory developed by, not all the theory, at least this theory developed by Gibbs, he assumed everything is spherical, yeah, which is far from reality, but for some reason it allows you to calculate delta G accurately for most of the systems that we work in the lab or also in the industries. So R is greater than RC. So all he needs to, all he tried to find is like, I know how molecules come together. I know how molecules might build some surface, but when it evolve into stable crystallite, so and he need to find some radius of that molecule, and which might evolve into a stable nuclei, and he need to find that sweet spot, and he wanted to find the radius of the critical nuclei. So this is how he found. So now we understand the diagram at the moment, so we can do some, how do you call it, we can do some derivation to to get the actual numbers. Let me check my notes. Yes, so this is what he calculated, this delta GS. This is nothing but the surface area of the sphere multiplied by surface energy. So this is the amount, surface energy, if you want to put it in the simplest possible way, this is something like the amount of energy that you need to keep that surface in some solution. Yeah? So if you want, you can call that as an interfacial tension. If you don't have that interfacial tension, it will dissolve back into that solution. So keep that in mind. So interfacial tension that allows to, that dictates your phase boundary. There are many ways to define surface energy and interfacial tension. Yeah? So from the crystallization point of view, this is something like that's the surface energy that exists between your solid and the solution. A few people or many books, they call this as interfacial tension. Gibbs called this as a surface energy. So this is something like to create some surface area, which is obviously of a spherical shape. The net free energy that you need to create some surface, which is nothing but the surface area of the actual sphere multiplied by the surface energy that allows to retain that surface to exist in that solution. So that's the simplest way to explain that. So we know the surface area of sphere is 4 pi r square multiplied by sigma. So that's your delta GS. And this quantity, if you remember, I said to you in this delta G diagram, this is going to approximately increase as a function of r square. That r square comes from here. And then we go to the volume part. Volume part is even very tricky. Just this is capital V. So this is nothing but the volume of your sphere multiplied by delta GV. So the net free energy to create the volume, or how do you call it, to be precise, something like the net free energy that we need in excess to that of bulk solution to create some volume, it's nothing but equal to volume of the sphere multiplied by delta GV. So in the above you see something like a surface energy, this part. Follow the pen, let me change the color. So this part, so here you will have something like delta GV. This, let's put small v. So this is capital V, this is small v. So what is this one? So this is the change in energy associated with the transformation process. So what does that mean? So in the above, you know that one, delta GS is something like surface area of sphere plus some energy that you need to create at that surface. But this is something exactly the same, delta GV. This is something like changing the energy transformation, which means you have some intermediate phase that creates from solution and eventually it transforms into some volume. So whatever the change in energy that happened here, so that will be reflected in this number. I hope you all how this gas, liquid, and solid works. I think if you have some gas, they will be far away. They will move randomly. When you convert them into liquid, they will move in its own space. So they will move together, something like this. All these molecules. So somehow you are arresting the movement of the molecules. So which means it has to lose some energy, and then if you make into solid, they are intact, which means you are completely arresting the movement of solids. So which means this energy will be even less. It will lose some energy. So you don't have to imagine these things. I'm just saying, like, we have this delta GV parameter because there is some transformation processes happening. So the energy associated with the change in fact the change in energy associated with the transformation process. So some energy will be minimized when you move from solution to something intermediate phase that have some definite volume. So that's how you have to keep these things in your mind. Yeah. So these are heavy duty thermodynamics. In fact, yeah, probably chemical engineers, they might have read this in chemical engineering thermodynamics, but and I'm sure at least the chemistry students, they might have studied something about free energy or also enthalpy of reaction. For sure they might know what's delta G mean. So delta G or free energy is something that defines the system. Something like if you have a liquid, that liquid is going to remain in liquid, and that's due to some fact that the liquid have some energy that can keep that liquid in liquid form. If you have a solid, that liquid have some energy, sorry, that solid have some energy to keep that solid in its solid state. So when you create some solid from a liquid, which means you have some energy associated with that solid and you have some energy associated with that liquid. So it's the same rule. If you create a new volume in that liquid, which means you are creating some new volume out of that solution, which means you are and that whatever the things which you are creating, it should have some energy to keep them in its own state. And whatever the difference between something which is created in that solution and whatever the energy that keep the solution in its solution phase, so that difference will be reflected in delta GV, provided that whatever the new structure which is formed, it has some 3D shape. In this case it's spherical shaped object. And what we are going to do is like we are going to substitute these values. We know delta G, which is nothing but the net free energy that you that we need in excess to that of the bulk solution to create a stable nuclei in the solution, is nothing but the delta G of surface factor and the delta G of the volume factor. So we can substitute this value 4 pi r square sigma plus the volume part. Oh, I didn't show this part. So volume of sphere here is nothing but 4 by 3 pi r cube. So if you remember in the delta G diagram, I say it drops even very faster. This is r cube. That's why it drops faster. It's delta G, this negative delta G is dropping, will drop more, how do you call it, drop faster and faster depending if the r value increased. If the r value increased by one factor, this delta G will be like r, if r is equal to 2 to the power of cube, so it will drop even more fast. So try to remember that. I hope you all understand this graph. So 4 by 3 pi r cube multiplied by delta G small v, so delta G. So from this we need to calculate RC. So how to do that? If you go back to this graph, delta G R, so this is the sum of your delta GS plus delta GV. So we have to find the R value or RC value, this particular point, critical radius. And we know what is delta G. So if we differentiate d delta G with respect to R here, and whatever the expression we get, we set it to 0. So that should give you the value of this particular point, RC. So why differentiating delta G with respect to dr should give RC? If you don't have mathematics background, I will try to explain it quickly. Imagine you have x, you have y. This is some function. Let's call it some function. What it says is like your y is increasing as a function of y, something like here, and it follows this some particular trend. So dy by dx. So this is change in y with respect to change in x is following some function, and that function looks like this bell curve. So that's the meaning. But if you look at this whole diagram, if you differentiate it, at this particular point, there will be some constant, and after, like, it will increase, reach a particular constant. After reaching that constant, it will decrease. So it will increase, reach this constant, and then it will start to decrease. Yeah. So this particular constant, if you differentiate a constant with respect to anything, that's going to be 0. So how do you differentiate? You differentiate 1. You cannot differentiate 1 with respect to something. That's going to be a 0 because 1 is some constant number. Yeah? So that's what we are going to do. So if you take at this graph, if you go back this graph, it's something is increasing and then it's dropping down. So we need to pick what will be this particular point. So there is some constant here. So if you differentiate this whole function, and then if you set the function to 0, that will give this particular value. So what do we mean? Like, we know delta G by delta R, it will be equal to some function here, some number 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 here. So delta G, the change in free energy with respect to R, is going to be some number at every point in this line, except at one point, and at this point it's going to be 0, because at this point the change in free energy with respect to R is equal to 0. Yeah? So just follow the pink line. So that's why we are going to differentiate this equation with respect to R. So I hope you managed to explain this. So let's give some equation number. This is 1, this is 2. So let's calculate the free energy that we need in excess of the bulk solution in order to create a stable nuclei. So that's nothing but delta G. This is equal to some surface quantity, some volume quantity. So we all know what is what. So delta G is equal to 4 pi r square into sigma plus 4 by 3 pi r cube into delta G small v. So what we are trying to do is like we know this relation delta G versus R, and then there is some peak maximum in this function. So this is nothing but R is equal to RC. So if the radius is greater than RC, then the nucleus will continue to grow. If not, it will dissolve back into the solution. So from this expression delta G, we are trying to calculate this RC value. Yeah? So what we are going to do is like we are going to differentiate delta G with respect to this with respect to the radius. So let's differentiate it. D delta G by dr, that will be equal to 8 pi r sigma plus 3 12 by 3 pi r square delta GV. So as I said, if you differentiate delta G with respect to R, d delta G with respect to R will be equal to some number at all these locations, all these points on this line, except at this particular point where it will be equal to 0. So which means delta G, the change in delta G with respect to R will be equal to 0 when R is equal to RC, which is nothing but the critical radius of the stable nuclei. So let's put this equation 1, this is equation 2, this is equation 3. So we set equation 3 is equal to 0, then 8 pi r sigma plus, so let's cancel this one, so plus 4 pi r square delta GV, that will be equal to 0. So from this we can calculate R will be equal to RC, yeah? Because we set the equation to 0. We know this condition. D delta G by dr will be equal to 0 when R is equal to RC. So let's calculate 8 pi RC sigma equal to 4 pi RC square delta GV. So this is 2 pi get cancelled. So RC sigma is equal to minus of RC square delta GV. So let's put this value. Sorry, this is 2RC. So 2 sigma by delta GV is equal to minus RC square by RC. So this gets cancelled. So therefore RC will be equal to minus 2 sigma delta GV. So the critical radius required to form a stable nucleus is minus twice to that of your surface energy divided by to that of the free energy required to form sorry, the associated with the transformation of from your solution to some volume. So RC, so let's give this some number. Let's put equation 3, and always remember RC is a constant. RC is a constant for a set of input conditions. So if you start with a supersaturation, say like supersaturation of 2, say RC is equal to, I don't know, let's put some number, say 0.1 nanometer. maybe 1 nanometer. If you start S is equal to 2, if you start your experiment with your initial supersaturation of 4, then RC will be less than 1 nanometer. So the rule or the relationship is like your critical radius is a function of your initial supersaturation but at a fixed experimental condition or if you want you can call at some fixed initial condition, say your initial supersaturation S is equal to 2 or 4 or 6, RC is a constant. So for each experiment your RC value is a constant. For each nucleation experiment your RC value is going to be constant, but your RC is inversely proportional to your supersaturation, initial supersaturation. So obviously you can perform different experiments starting from different initial supersaturation, and this RC value is going to change. So that's how the nucleation works. So try to remember these things. I might ask some objective type questions based on this line. So this is not a mathematical rule. RC is inversely proportional to 1 by supersaturation. This is an experimental fact. In fact, if you do some experiment with this solution, S is equal to initial supersaturation of 2 and then S initial supersaturation of 4, and then you go home, you come next day, and if you check the size of the final crystals, the size of the crystals that you get from this solution, if this is like say 4 microns, so from this one you will get 8 microns. This is some approximately. So what does that mean is like it will also produce, if you start with a higher supersaturation, your the critical radius of the stable nuclei will be small, and also the size of your final crystals, it will be reflected in the macroscopic properties of the final crystals. That will be less when you compare with some experiment that you begin with a supersaturation which is comparably smaller when you compare to the second experiment. Yeah? So something like these are the experimental fact, and these are some theoretical fact. RC is inversely proportional to your initial supersaturation. So what does this mean? This is not even a relationship. If you want, we can call this as a trend. How the trend of RC changes with your initial supersaturation. So that's what the meaning of this equation. So if you want, I can write it here. It also means higher supersaturation, or higher the supersaturation, lower will be the RC. So which means the critical radius, or the number of molecules required to form a stable nuclei will decrease. So that's the meaning of all these things. Yeah. So let's keep it like that, and in fact we have some relation, some correlation that allows you to relate your critical radius with your initial supersaturation, or in general supersaturation. So it was proposed by two guys, Gibbs and Thompson. It's called the Gibbs-Thompson relation, in fact. Yeah. So they gave I will call GT, gave an expression to correlate the experimental condition. Yeah, why I say this as experimental condition? Because Your supersaturation is some quantity that can be easily measured. Like in the laboratory experiment, I used FTIR to monitor concentration, and from concentration I can calculate my supersaturation. Yeah. So experimental condition S with RC, and is given by, so ln of S is equal to 2 sigma KT divided by R, or in particular RC. So sigma is your surface energy. This equation has some few new parameters. So T is your temperature. Temperature also plays a big role in the experiment. Yeah? So which means, and then K is your Boltzmann constant. Boltzmann constant is extremely a small number, something like 10 to the power of minus 28. And then V is a molecular volume. So it also depends on the molecule as well. Yeah? So let's give this equation some number. Let's call it as 4. This equation is fine. Let me check what's my equation numbers. I lost the track. So this is equation 4, and RC is equation 3. This is equation 4. So far we calculated, or at least we have now something, the relationship between RC versus your supersaturation. So this is your this is something that can be measured, supersaturation. So this is measurable, or if you want we can call it as observable. So this is something we can measure. And then what else we calculated so far? We calculated the critical radius RC, which is equal to 2 times your surface energy divided by the free energy associated with the transformation. So we have this one. I think I gave some number for this. This is equation 3. So now if we go back to this free energy plot, this delta G, this is delta G positive, delta G negative, this is delta G equal to 0, R in the x-axis, and then delta G in the y-axis. So we know how to get our RC value. So which means if we have RC value, we can also calculate the free energy required to form a stable nuclei in the solution, or how do you call it, the free energy that we need in excess to that of bulk solution to form a stable nuclei. We can calculate that. So how to do that? So we already know from equation 1. This is slightly bigger derivation, sorry for that. So delta GS, delta GV. So if you're going to write an exam like normal day, like if you come to university and if you're going to write the exam in presence of some I don't know how to call, like invigilator, I might ask this derivation in the final exam. But now, since it's going to be open book test, your final exam, you have to understand the concepts, and then I'm going to ask some questions which you can answer only if you understand the concepts behind nucleation. So try to pay attention to all these derivations, and whenever I say that's the relationship between supersaturation, critical radius, you should have some idea what I'm talking about. So we know this value is 4 pi r square sigma plus 4 by 3 pi r cube delta G small v. So I think I stated this as equation 3. So what we are going to do is we will substitute equation 3 into, so delta G will be equal to 4 pi r square sigma. What I'm going to do is, like, I'm going to substitute the delta GV value here, which is in equation 3. So this one I'm going to plug it in equation 2, so plus 4 by 3 pi r cube. So delta GV is minus 2 sigma divided by RC. So let's expand this one. This is very easy to solve. So before this we have to mention something. So we have this equation 2. So this is something like delta G as a function of R. So what will be this value, delta G critical? Delta G critical. So you have this free energy plot. So this is your RC, this value. So if you put a line here, that will be delta G critical. So that will be the critical free energy that you need in excess to that of the bulk solution to create a stable volume and a surface, yeah? Or in other words, to create a stable nuclei. So this one, so let's strike this for the moment. We will come back to this. So in equation 2 we can substitute R is equal to RC. So when R is equal to RC, delta G will be equal to delta G critical. So let's put these notations in equation 2. So delta G critical will become 4 pi RC square sigma plus 4 by 3 pi RC cube delta G small v. So let's call this as equation 5. So we are going to substitute equation 3. RC is equal to minus 2 sigma by delta G V. So this one here in equation 5. So delta GV will be equal to minus 2 sigma by RC. So delta G critical, so we are going to plug in this value in the delta GV here. So will be equal to 4 pi RC squared sigma plus 4 by 3 pi RC cube, and then delta GV is nothing but minus 2 sigma by RC. So this is easy to expand. I will do it very quickly, it's not tough. So 4 pi RC squared sigma plus, so 4 into 2 minus 8, so minus 8 minus 8 pi RC cube multiplied by sigma divided by RC. Yes, that's perfect. So this one will get cancelled, so you will get by 3 here. So 4 pi RC squared sigma minus 8 by 3 pi RC squared multiplied by sigma. So we take a common factor here, 3 fours are 12 pi RC squared sigma 8 pi RC squared sigma, that will be equal to 4 pi RC squared sigma divided by 3. So this is your delta G critical. So that is the amount of free energy that you need in excess to that of your bulk solution to create a stable nuclei, or in order to create a phase change in the solutions, like a solid, to create a new solid in that solution. Yeah? So hope you all get this one. So if you look at this value, RC we cannot measure very easily. Surface energy, it's not an easy task to measure. So we do not have any parameter that you can get from experiment, like for example supersaturation. So but we have the Gibbs-Thompson relation. Gibbs-Thompson relation that relates RC with that experimentally measurable quantity, which is your supersaturation. So we all know this Gibbs relation. Where is that? So ln of S is equal to 2 sigma divided by KT RC. So these things we know. So what we are going to do is like so therefore RC is equal to 2 sigma divided by KT into ln of S. So let's call this as equation 6, and then we substitute this RC value from equation 6 to here. So from that we can get delta G critical. So delta G critical will be equal to 4 by 3 pi. RC value is 2 sigma V by KT ln of S the whole squared multiplied by sigma. So that will be your delta G critical value. So how to do this? So this is equal to 4 by 3 pi 2 square is equal to 4, and then sigma squared molecular volume to the power of whole squared multiplied by sigma divided by KT ln of S the whole square. So this will be equal to 16 pi sigma square molecular volume to the raised. So this will be sigma cube, because you have sigma square multiplied by sigma divided by 3 KT ln of S the whole square. So this is your delta G critical, something that related to your supersaturation. 3 KT ln of S the whole square. So I hope you all remember V is molecular volume. Molecular volume, KT is Boltzmann constant, T is temperature, S is supersaturation. If you know all of this value, then we can calculate delta G critical. Yeah? So this expression is very important expression, and this is one of the most used expression in industry wherever they are using crystallization to purify some compounds. Yeah? In the industries, they use this equation to calculate nucleation rate. Nucleation rate. Also in academic laboratories, we use almost every day. Nucleation rate, that's the notation J. So the unit is like numbers per unit volume. If you express the reactor volume in liter, so it will be like some number per liter. So what is this? You have some solution, say supersaturation 4. Imagine it suddenly nucleated, which means you will have millions and millions of crystals. So J is nothing but the number of nuclei formed per unit volume of solution, also time, per unit time. Nuclei formed per unit volume of solution per unit time. So this is some number per liter per second, something like that. So J is nothing but equal to some pre-exponential factor, exponential of minus delta G critical divided by KT. So this is called a classical nucleation theory. This was developed in 1950s, and still this is the only expression that we have. So what it says is like the nucleation rate is proportional to your delta G critical, where your delta G critical is a function, this is a negative value. Just remember this negative value. Okay, maybe I will substitute and then you will get some idea. So let's give this delta G critical is equal to 7, this one equal to equation 8. So substitute 7 in 8, we get J is equal to A into exponential of, just put the whole value, 16 pi sigma cube molecular volume raised to the power of cube divided by 3 kT. So we already have kT here, so let's put k square t square multiplied by ln of s the whole square. Sorry, k cube t cube. Yeah, because you have kt square t square multiplied by this kt, that will give you k cube multiplied by t cube. So this is the classical nucleation theory. Extremely important theory we use in lab every day. The industry people, they use it almost every time when they are trying to purify some compound using some nucleation. So what this J states, J is like some number of nuclei formed per unit time per second is inversely proportional, is proportional to your supersaturation. So you have a negative symbol and you have your S is in the denominator. It means J is proportional to supersaturation, yeah, automatically. So if you have a higher supersaturation, then the number of nuclei that formed per unit time is going to be high, yeah. So that's the meaning of this this expression. So what I will do is like I will try to solve some problem using I might give some function for J, and then I will give some supersaturation value. I might ask you to calculate something like surface energy, for example, or I might give the surface energy, I might give the supersaturation. So I might ask you to calculate the nucleation rate based on these values. So I will take some values that we already got from the lab. So I will give you, I mean, this is not for your laboratory report, this is for your final exam and also during the tutorial time. So what we learned so far is like we learned a lot about crystallization. We know crystals are a macroscopic object and it's composed by unit cell, and you know how the crystals are formed in solution, and we already learned a bit about supersaturation, and then we also learned about metastable zone width, and then from metastable zone width I showed some how to use that graph in order to identify some conditions where you can expect nucleation or where you can grow the crystals. Yeah, so those things we learned already, and then we learned all the basics like how the crystals grow at molecular scale level, and then I showed through some diagram how the supersaturated solution looks like and how the saturated solution looks like. We learned a bit of all of these things, and then finally I came to this theory because we cannot leave crystallization without reading the basics of nucleation. So you must know this nucleation concepts and you must know the nucleation theory. So this is the only theory you learn in the topic of crystallization through this module. I think this is enough. I think, and we also derived the very important theory in crystallization, which is the classical nucleation theory. And then I also explained the concept, how Gibbs imagined how the molecules assemble to grow, and when it grows, when it dissolves back in the solution, and both of these events are dictated by that sweet spot connected to the critical radius of your nuclei. And if once the nuclei reach the critical radius, it will evolve into a stable phase. If not, it will dissolve back into the solution. And we also know how to calculate this critical radius through the Gibbs assumptions. We assumed some surface factor, we assumed some volume factor involved, and then we sum this value to get the free energy that you need in excess to that of bulk solution. I also said in somewhere like every solution remains in its state, or everything remains in its own state, because everything associated with some energy. So everything is there due to some energetic state is there, yeah? And then you have to surpass that energy value in order to create some new phase in that solution, yeah? So that's what we call it as delta G, and you need to create a stable volume. That's a spontaneous process, that's what I explained. And then the surface, the system needs to do some work out of those spontaneously arranged molecules to create a stable surface. And then we know how to, and this one will change with respect to your radius except at one point. And so we differentiated that expression d delta G with respect to r. That's how we calculated this RC value. And then I showed you the relationship of Gibbs Thompson, how he related the critical radius with the supersaturation. Supersaturation we can measure through experiment, while RC nobody knows. We have to calculate it through some equations like what we derived so far. And then what else we learned? We substituted this RC value in the delta G, which was originally developed by Gibbs, and then from that we got some relationship which we call it as delta G critical. This is equation 7 here, and then from that we finally got I showed what's the classical nucleation theory, which is a simple expression, which this is something like a number of nuclei formed per unit volume per unit time is equal to some constant multiplied by some exponential of whatever the delta G critical we calculated using the Gibbs expression. So I think this is enough for this module. And then the next video is going to be something about your lab. I will tell what are the things we learned in the theory, like metastable zone width, supersaturation ratio, and why I fixed some supersaturation ratio, and how I performed the growth experiment, and what does mean by this seed loading, 50% loading, 80% loading, and what are the seed size that I used. So those are the things you are going to learn in the next video. So far what we learned in part 1, like in crystallization, I'm going to upload it like a 3-part something like a part 1A, B, and C. So all of these are something related to crystallization basics, and then part 2 is your actual experiment, that how we performed in the lab using part tools, and then part 4 is going to be the details of your experiment. So we covered the crystallization topic completely in this last 4 videos, I think 4 or 5 videos, I don't remember exactly. But and then all we left is like something about the crystal growth that you will learn through that experimental data which I'm going to supply. I didn't post it in Solis because I didn't teach you how the crystal growth actually works. Yeah? So once I did that, I will post the data, and then I will also give the instructions what to do with your lab report plus assignment. Yeah. So I think I'm going to stop now. Thanks for listening.